Hello, Physics 2 people. Welcome back. In this video, I want to discuss Maxwell's equations, and I want to recast them as differential equations rather than integral equations. It just gives a kind of a different perspective on what we've been doing all semester long. To do this, we need to remember some results from Calc 3. And if we were meeting in person, one of the goals with math problems of the day was to have you derive some of these results. In Calc 3, you discussed various forms of Green's theorems, and they related things like the divergence across an area to an outward flux through the surface or through the line segment or the perimeter of an area. And then there was another one which related a curl integrated across the area with a circulation around the boundary of it. Well, here we actually need the 3D versions of these things. So the 3D version of the divergence theorem is written as follows. For a nice vector field, we'll just call it V. When I say nice, I mean it's differentiable, it's smooth, it's just reasonable. It has compact support. It doesn't go off to infinity. It kind of is localized. We have the following. We get that the integral of the divergence, so this del dot V, remember you have the gradient, you can take cross and dot products with it on vector fields, integrated over a volume is equal to the outward flux of the vector field. And then we also had that, so this is called Gauss's theorem. Not to be confused with Gauss's law, and we're going to use Gauss's theorem when we rewrite Gauss's law, but they're two different things. Then we also have Stokes' theorem, which says that the integral of the curl of a vector field, the flux of the curl of a vector field over a surface equals the line integral, or the circulation of the vector field around the boundary of the surface. So for Gauss's theorem, you have an integral over a volume equaling an integral over a surface. For Stokes' theorem, you have an integral over surface equaling an integral over a curve. All right. So now we're going to use these to rewrite Maxwell's equations. The other thing I want to say is things like you can write, we can rewrite charge as the integral of a density dV. So things like that. Okay, so let's start with Gauss's law. So Gauss's law in integral form says the integral of the electric field, the flux of the electric field over the surface equals Q over epsilon naught. We can use Gauss's theorem to rewrite this as the integral of the divergence of E over the volume equals the integral of the charge density over epsilon naught over the volume. Or I can rewrite this as the integral of del dot E minus rho over epsilon naught dV equals 0. Just subtracting the charge density over to the left-hand side. Now, this is to be true for all regions, all geometries. So the only way you can have an integral over volume equals 0, no matter what volume you choose, is if the integrand must be 0 itself. So we learned Gauss's law for electric fields can be rewritten in differential form as del dot E, so the divergence of the electric field equals the charge density over epsilon naught. Similarly, for magnetic fields, we could just say the divergence of the magnetic field is 0. That's Gauss's law for magnetic fields. Let's take a look at Faraday's law. That says the integral of E dot ds equals minus integral and where I've kind of anticipated where I want to go, and I moved the partial derivative to the inside of the integral. All right. Now, using Stokes' theorem, I can write the left-hand side as follows. Or subtracting the right-hand side over, I can say that this must be 0. And this must be true, this equaling 0 must be true for any surface we choose. Therefore, the integrand must be identically 0. So Faraday's law can be written as the following equation. Stating that the curl of the electric field is minus the time partial derivative on B. We can do the same thing for Ampere's law, and I'm going to write all of Maxwell's equations in differential form in one place. Okay, so we have Gauss's law, so we get del dot E rho over epsilon naught. And then we have and for the Ampere Maxwell's law, we get del cross B equals. Now, you don't get current, you actually get current density. And we have plus mu naught epsilon naught. Okay, so this is the differential version of Maxwell's equations, and just some comments. Um, if you think about where these came from, Maxwell's equations started out as integral equations. So these were relationships between something happening over an entire area, equating to some charge, or um, maybe something happening over an entire area equaling something that happens over an arc length equating something over an area. These were spread out over space. These are non-local integral equations. Rewriting them with Maxwell's equations in differential forms gives you local statements. These are true, these are derivative equations. These involve information that is defined at each point separately. So this is the local version of Maxwell's equation. So you have these are equations which are true at every local point in space and time. Other observations, you see things like magnetic fields create electric fields, but then electric fields create magnetic fields, which create electric fields, which create magnetic fields, which create electric fields. So there's definitely a sense in which you get that one field creates another field. Okay. The other reason these are really nice is that as you guys are learning, there are many techniques for solving differential equations. And although these are partial differential equations, these are partial vector differential equations, and they're quite complicated, there are lots of techniques for solving these using computers and otherwise. And so for any further study of electricity and magnetism, these four differential equations become your stepping off point for solving any other problem, basically, other than the few that we've studied through this semester. All right. In the next video, I will show how to pull together these equations and look at oscillatory wave solutions to these equations.